Everybody. Welcome to Rod's Office Hours. We're going to share some oil industry insights. Um, it's great to be back after a couple of delayed weeks. So got something pretty interesting tonight. It's in the well integrity space. We're going to be talking about surface controlled subsurface safety valves, which is a pretty big mouthful. SCSSVs is the abbreviation, and it is a device that has really improved safety in the industry, safety and environmental impact. So we're gonna talk a bunch about that tonight. So, what is SCSSV? Well, I mean, this is really around innovation and continuous improvement. I'm going to explain how here in a second. A surface-controlled subsurface safety valve is a fail-safe device. So, and a fail-safe device is basically any device that, if it has a failure, it puts you in a safe position. So, most valves, like a regular valve that a gate valve or globe valve, any sort of valve, if it fails, like it doesn't work anymore, whatever position it was in, it stays there. Whereas for a safety valve, surface control safety valve, if there's an issue, any sort of issue happens, it fails closed. So it makes the well safe. So it's placed in the well, and if there's a issue topsides, it'll fail closed. So, and we'll get into how it operates, how it works, and that. But really, to talk about surface-controlled subsurface safety valves, we really can't talk about it without talking about offshore development and innovation and learnings. And so you can see here is a offshore platform with hydrocarbons bubbling up around the platform, also offset from the platform. And this black stuff is oil in the ocean where you don't want it. So we'll talk about how this has led to this innovation. A little bit about myself. My name is Rod Gibbons. I'm a petroleum engineer and entrepreneur in the oil industry now for 30 years, probably a little bit over 30 years now. Together with my wife, Willow, we make doing business in the industry better. That's our goal. So, and I've had the privilege of working in multiple countries and work environments, and hope to share some of my insights in working around the world and different places, onshore and offshore, that you might not hear elsewhere in school or wherever. So, yeah, I'm going to share my insights. So that's me. Now, let's talk about Santa Barbara. You probably didn't think I was going to say Santa Barbara, California. If you remember a few weeks back, we had discussed where in the world oil and gas is, and it's basically everywhere. Well, one of the oil in the U.S. really started in sort of the east in Pennsylvania, but it didn't take long for there to be oil discovered in California. And so we're going to focus on Santa Barbara because the platform we're going to talk about is Santa Barbara A. So it's in the Santa Barbara channel. And this is just north of Los Angeles, next to Hollywood, Pismo Beach. San Francisco's up here. So think of really stereotypical California type beachfront. So when you have that image in your mind, then if you look back to what it was at the turn of the 19th century, this is what the beach looked like in 1905, where oil had been discovered onshore California, and as you can see, they had made it to the beach, about to finally go out to these piers. So, very different world than our stereotypical thinking of California. When you look at current wells, so this is Ventura, California. Santa Barbara's up here. You can see all these dots are oil and gas wells. So there is, Malibu is down here. There's a naval base. So I guess and again, we've talked about it before, where there's oil and gas around the world. We focus in on California in the sort of late 60s, early 70s, thinking of that culture and what was going on in those cities. Oil development is pretty far out of the picture of that time period. But you can see lots of activity historically in California, onshore, excuse me, and offshore as well. So you can see that quite a few platforms, onshore facilities. So here in Santa Barbara, you can see there was quite a number of platforms, and platform A was installed in 1968. And so, but even still, there's still oil and gas development going on offshore California today. So there's currently a number of offshore facilities, production platforms, and as you recall, we talked about production platforms with drilling derricks on them, and all these pictures have it. So all these rigs will have wells and drilling and workover capability. So, but there's over 30 rigs currently offshore California, which again is a fairly active area, but it's not something that we think of when we think of California, or that we think of oil and gas. So, but specifically, I want to talk about Santa Barbara A platform. And so again, we're looking in California, we're looking in Southern California, just north of Los Angeles, offshore. And this is the Santa Barbara Channel, Santa Barbara A, and fairly close to shore, with other platforms and facilities here. Well, the thing about Santa Barbara A platform is that in 1969 there was a blowout there, and so this is this picture from early in the presentation. So you can see what had happened here was they were drilling from the platform, and they had drilled down to the reservoir section, and had taken a kick, which is influx of hydrocarbons, and they closed their BOPs, and we talked about blowout preventers or BOPs on drilling rigs. But because there wasn't a lot of casing in the well, the actual rock cracked, and then you had oil and gas coming up, went out into the rock, and then came up at the surface. So this was an uncontrolled release, of what we normally call a blowout. And just to come back on well construction a little bit. So we've got our reservoir formation. We'll drill down, and we spent some time talking about drilling before. So we drill our hole, we set casing and cement them in as we're drilling deeper. And then we'll run tubing with a packer on here so that flow will go up the tubing and for production after we perforate. So that's our normal well construction. But sometimes that doesn't always go as planned. Even with the best planning, you can get a blowout. And because if you remember I call it our formula, the only formula we need to know, which is that pressure equals density times gravity times height. In the video, this is a land rig. I think it's in South America, and you see a bit of gas coming out here. Some people running around. So here we're looking. The BOPs would be down here. And here's the drilling derrick and pipe. If our density, if the reservoir pressure, if our mud density is too light, you'll get a naturally flowing well. We like it when we're producing, but when we haven't put a Christmas tree on or done any of that stuff, this is an uncontrolled release, a blowout. And so here on shore, you can see that there's quite a gusher of oil and quite a mist of gas. So, and again, we're flowing naturally here because the reservoir pressure is higher than our density times gravity times height, and that's causing the blowout to occur. So this is what you don't want to have happen. And then here in this situation, it has finds an ignition source and catches fire. So, which didn't happen in Santa Barbara. It didn't catch fire, but it was a bit of a different consequence. But again, go back to our old formula about hydrostatic pressure. Again, well control is something that is a discipline in petroleum engineering to itself, but really what you're trying to do is have enough density in your fluid so that you don't get a naturally flowing well when you're not ready for it. So what this looked like in Santa Barbara, so this is an offshore platform. You can see this, and this is 1969, so this is a black and white picture. So, but you can see a pretty good oil slick here. Again, same as in that land rig, the reservoir is flowing, it's lifting the fluid out of the well, coming to surface here to the sea floor, and then the current takes it away offshore. Sometimes you can get a fire happen offshore, but just in this case, just the nature of the gas and the low, nature of the oil and the low gas content, it becomes an oil spill as opposed to a fire. So and this has happened in the past. There's been a number of events, and just to put it in frame of reference, Deepwater Horizon was a deepwater drilling rig in the Gulf of Mexico that in 2010 spilled almost 5 million barrels of oil into the Gulf of Mexico. So that's a lot. But there is a number of events that are of the same sort of scale. There's in 1991 the Kuwait oil fields. This was when Saddam Hussein was pulling his troops back out of Kuwait. They sabotaged a bunch of the wells, and there were 6 to 8 million barrels of oil released in blowouts. 1989, Exxon Valdez, there was a tanker spill, 750,000 barrels. 79 was another spill. 1969, Santa Barbara, Platform A, the spill was 100,000 barrels, which was about 2% of the volume of Deepwater Horizon. So looking at it from historic point of view, it wasn't an immensely large volume of oil, historically speaking. It was still 100,000 barrels. That's a lot of oil. But compared to Deepwater Horizon, or the 1910 Lakeview Gusher, which was 9 million barrels, almost double what the Deepwater Horizon spill was. And that was in Kern County, California as well. So, and I did find some old pictures of that. So this is Kern County by Kern River in California, which is really nice country. But here, this looks like a river, but this is actually oil coming out here. This is in 1910. And then there was also lakes created to try and contain things. Again, the reservoir pressure being higher than the hydrostatic, it just keeps flowing. Just a question in here. Learn in this presentation that an SCSSV is a safety barrier in an offshore well. My question is, are there multiple types of well control barriers used on an offshore platform, or do you choose one? Well, that's a good question. And we'll show some of those further on in the slides. But as engineers and as oil operators, we are responsible for ensuring we have the appropriate level of safety devices in our wells and our facilities. So a subsurface safety valve, a surface controlled subsurface safety valve is pretty well industry standard in offshore wells. In some land wells, they're also required by regulation. So if you have a onshore well that is a critical sour well, so a very high sour gas, poison gas concentration, that might have a extra fail-safe device in it. And there's some locations where there's actually two subsurface safety valves installed. So again, I would say industry standard is offshore wells will have all offshore wells would have surface control and subsurface safety valve, and most onshore wells not. And we can get into the workings of that a little bit further on. Good question. But back to 1969, our Santa Barbara spill. Here you see the Santa Barbara platform, and you can see there's quite some disruption offset from the platform, again because of a breakdown in the shoe below the casing. So the oil was fairly heavy, and again, this is from a newspaper showing here's the oil rig, here's the town of Santa Barbara, here's Ventura, California. So the oil followed the current and made landfall by Ventura. And but again, if you think of the place and the time, that this was a impactful event. So because Santa Barbara, this is one of their promotional posters. It's where because it was just north from Hollywood, it was where the people in charge of media and a lot of famous actors and movie stars, this is where they went to vacation. This is where they went to relax. So when you've got that sort of place and that sort of people's attention, well, here's platform A, here's the active oil spill, and you can see that the oil has made it to the beach and it's being put into barrels. There's a bunch of hay that's being mixed in with this sort of heavy crude to try and contain it and clean it up. So that is a very It's a pretty big, any spill is a big deal, absolutely, from an environmental point of view. But from a perception point of view, this is the livelihood of that community, and this is not the image that they want to show. So I guess it's sometimes hard for us to imagine what industry norms were and how things have evolved over time. And so I think if this happened today, there would definitely be some maybe a bigger response than sopping up the oil with hay. And I think there's much more environmental awareness than there was in 1969. So so this was Union Oil, and the president was a man by the name of Fred Hartley, who was a trained engineer with Union Oil. And so there's Mr. Hartley. And this quote, which ended up getting quoted in the Los Angeles Times, was I think reflects the attitude at the time, which is, I don't like to call it a disaster because there has been no loss of human life. I am amazed at the publicity for the loss of a few birds. So that statement is these days quite shocking, I would say. So there's just a chat in here. Sorry. Yeah, it is funny. It's funny because of the context in this context, in this man's context, he just saw it as the loss of a few birds. So again, given the setting, but what was the response to this as an industry and as a society? I think two notable things happened. One was the innovation of the surface controlled subsurface safety valve, which can be I have to put this in somewhere. This is a great slide for it. It can be SCSSV or SCSSV, because depending if you do two S's for subsurface or not. DHSV, downhole safety valve, or tubing retrievable surface controlled subsurface safety valve, or WR, wireline retrieval. So anyway, whatever type of abbreviation you use, the industry innovated and came up with a fail-safe device for use in wells. And I know there was a lot of environmental concern at the time, but one of the triggers for the modern environmental movement was this Santa Barbara spill. And so the first Earth Day was actually organized in 1970, when at the end of the semester, when after this happened. So you can see there's a societal movement and a technical solution. So so maybe Mr. Fred helped us more than he thought. So well, let's get back to the engineering bit. Again, when we look at our formula that we like to use all the time when we're talking about wells, pressure equals density times gravity times height. And if we get this IPR curve, the inflow performance coming into the reservoir, and we got to intersect it with the tubing, we're going to get flow. So, which is normally exactly what we want, but not when we have an issue at topsides, at surface. So this diagram it might be a little bit complex, but really, so this is a well barrier diagram. So we've done well cartoons, well schematics. The difference with a well barrier diagram is you can see there's an outline in blue and there's an outline in red. And what that signifies is our primary and secondary barriers. So we have our reservoir with our reservoir pressure here and our perforations. That energy is coming into the well, and you can see the blue line is what's containing that pressure. That's our primary barrier. If any element in that system fails, then the red line will still contain the pressure and still contain the oil so that you don't have a release. And so we've talked about a bunch of these things before. You can see the casing and the cement and the tubing and the Christmas tree and the Christmas tree valves and the wellhead. But this little symbol right here, which is like a flapper valve, this is our downhole safety valve. So this is the valve that's going to hold back if we were to lose our Christmas tree or get a leak in our Christmas tree. And again, the thinking was, what happens if a ship comes by and impacts an oil platform and gets rid of this Christmas tree? Then we have no control. The downhole safety valve, that is our fail-safe mechanism. And I should note that some places this is considered a barrier, some places it's a fail-safe but not a barrier. So in some jurisdictions, this is the thing. But back to Willow's question, most jurisdictions, this would be a standard by API standards or ISO standards. ISO 16530 talks about well integrity, international standard, as well as NORSOC, which is Norwegian standards, D010. They're all very helpful in laying out what you should be designing when you're putting your well architecture together. So this is, again, following Santa Barbara, the innovation was we can't depend on fluid columns. We can't depend on our casings to hold all the time. Let's give ourselves some mechanical help so that we have a fail-safe device. And so again, this is not a barrier diagram. This is more of just a wellbore schematic, but you can, same sort of principle. Hydrocarbons come into the tubing. This SCSSV, I guess that's another abbreviation, is drawn as a valve across here. So that's what it looks like in cartoon form. In actuality, it is a flapper valve. And so it's like a check valve. And so I happen to have one here. Here's a flapper valve. Like you see this gold piece here. And so when the well is producing, this flapper valve sits behind the sleeve out of the flow. So now oil and gas can flow up the tubing. When hydraulic pressure is lost, there's a spring force that causes this flapper to close, and that shuts off any flow from above. So that is a flapper valve. That's another name for these things, because surface controlled subsurface safety valve is so hard to say. So, and it's surface controlled because there's a hydraulic line from surface. That's what controls it. That's what keeps it open. If there's an incident at surface on a platform or subsea where you lose hydraulic pressure, could be that something hit it, could be a emergency shutdown, it could be lots of reasons. But if you lose hydraulic pressure, that valve is going to close. Another question in here. Do I understand clearly that safety is needed because the oil is never in control, but with the SCSV it stays in control, but not for stopping the oil, but to control? No, I guess the oil is normally in control. So let me just go back a slide here. Normally, in this diagram, this valve is open. We've got hydraulic pressure on there, and we've got that flapper open. And our oil is flowing up to our Christmas tree. And it doesn't matter if it's a subsea Christmas tree, an offshore platform Christmas tree, or an onshore Christmas tree. We control the flow of hydrocarbon using the valves on our tree. So this one shows the master valves and wing valves. There's also a choke here that we can open and close so that we can adjust the flow or close the well in. That's what we're using our Christmas tree. That's what our Christmas tree is for. It's just a collection of valves to control the flow of fluids. The safety valve, the safety valve, we don't control the flow with this. We don't adjust it and say half open, half closed. This is entirely a safety device. So it's going to slam shut. So and we'll see that in the video coming up, how the thing actually operates. But it's an on-off. So it doesn't control it. It shuts it in. It's your emergency brake. So a couple of pictures here. So this is a cut. This is a cutaway. So normally this is a full. It looks like pipe. Like most of our downhole tools that we've seen, they're all round and look like pipe because they all have to fit inside another string of pipe. So, but the principal operation here is, and this is sort of drawing wise, animation wise, you have hydraulic pressure comes in, pushes on this piston, which is connected to this sleeve, this yellow sleeve. And that would be this sleeve here. Then, excuse me, as you pressure up with hydraulics, it pushes that sleeve down, and it's going to push that flapper out of the way. And now you're open, you can flow. If for any reason you lose hydraulic pressure, then that's the signal that we're sending downhole that we have an emergency at surface. When that hydraulic fluid pressure is gone, this is a spring. So we pushed that spring down as well. As we pushed everything down, then as soon as we lose the hydraulic pressure, that spring pushes that sleeve up out of the way, and there's another spring on this flapper that closes. So, and we'll see that, just a little video of it here, or animation, sorry. This red line is the control line. That's strapped to the outside of the tubing. Then it's screwed in. This is the safety valve body. This green is the sleeve. And you can see there's this spring in place. And the blue is this flapper. So now, pressure up with hydraulic fluid. And we're pushing that spring, that sleeve down, compressing that spring, and opening the flapper valve. Here we see it again. See, it's popped that sleeve, that flapper open. And then we lose hydraulic pressure. The spring force lifts the sleeve back up. We go pushing it down. It opens the flapper, pushes it out of the way. And then when we lose force, the valve, comes back and closes. And then oil, gas from the well can't make it past this flapper. It's sealed off. So that way, we're using hydraulic pressure to open it. So we're controlling it from surface. Surface controlled, subsurface safety valve. So we put this thing down in the well. So that way, if a currently working here in the North Atlantic, if an iceberg hits a Christmas tree, this valve is still in place. It's below the mud line. And you can see, and then when the sleeve moves down across the flapper valve, it also protects this valve doesn't see any reservoir fluid. It's protected by the sleeve. That way it's ready for when it needs to close. So during normal operations, usually these valves are have hydraulic pressure on them continuously, and once every 6 months during normal operations, once every 6 months, you would do a test, an inflow test, where you actually bleed the hydraulic pressure off and make sure that the valve this valve still holds reservoir pressure back. So, and they can be they're very reliable. They're built to be reliable. So that was an animation. This is an actual test. This video is an actual test. And again, they've cut away the side of the valve. Normally this would be a full 360 pipe, but they cut it away so that you can see what's going on inside. This was, I think, Norsk Hydro, which used to be Equinor. So they're just using a hand pump to pump this, so it doesn't go that smooth. So you see he's pumping that with the hand pump, applying hydraulic pressure. See this? You can see that round is the flapper valve behind. And so they get it down. Hydraulic pressure pushes that sleeve down. Then when he bleeds off the pressure, this thing is going to, you'll see how fast it happens. Now. So this is a real world example. That's actually what happens. Now, we don't usually use a hand pump. There's usually like a hydraulic pump at top sides. But for demonstration purposes, you can see, again, that hydraulic sleeve gets the flapper valve out of the way so you could flow. Then if you had a problem with your hydraulics, you can lose pressure and shut in the well. So this innovation has prevented, well, I don't know how much environmental damage. It's hard to compare the innovation of the subsurface safety valve and Earth Day. Both are good, but this is a good engineering solution that the industry has really created and adopted. And again, it is a standard piece of equipment that we use. So I say it's standard, and now I'm going to show you there's a lot of different types of safety valves. So there is a type here that's actually, rather than a flapper, it's got a ball. So works on the same principle, but it's just a ball rather than a flapper. You don't see too many of those, but they do exist. The ones that we've been seeing are all tubing retrievable. So they'd be TR SCSSVs, which means they are screwed in to the tubing string. So when you would run your tubing, you would actually screw a safety valve in there, and you'd run a control line alongside and band it on as you go. And so it's integral to the tubing. Another option this is a wireline retrievable safety valve. And so in this completion, there was the valve wasn't necessarily run, but there was a small nipple with a profile that was run and the control line attached to it. This safety valve you can pull with wireline, so that if you have problems, you can actually just go in with wireline. You don't have to pull the whole completion. You can just wireline retrieve this valve and run a new one, and it'll land in the same wireline locks. And so applications where you want to do that would be if you had a lot of sand production, for example. You think, well, I'm probably going to wear out this valve very quickly, so I want to change it out regularly. Or there's also an option where if you've run a tubing retrievable safety valve, if it fails, you can actually install a wireline set valve. There is the way the tubing retrievables are made. They're made so that you can lock them open and install a new valve. That does restrict your tubing size, but it does. Then you don't have to change the completion. And again, just looking at the components, the main components is hydraulic control line, your rod piston, which pushes down your flow tube. I've been calling it sleeve, but I guess the correct term is flow tube. And then your power spring, you compress that. That's where it moves it up. And then your flapper, which is the really fun part. This is, of course, for 7-inch tubing. So this is, I think, probably as large as they make them. So, but pretty cool. And then just a note on setting depths. Surface controlled subsurface safety valves. So there's a platform. Here's the mud line or sea floor, or on land, ground level. And so in this example, there's a subsea tree, or going back to a platform. Your surface controlled subsurface safety valve is below the mud line. And again, you want to have that below the mud line so that in the event of a catastrophe or disaster that happens in the water, then you still have your fail-safe device is protected, because it can be 100 meters to 1,000 meters below the bottom of the ocean, so that it still stays in place and it's gonna stop that reservoir. Just checking. And then another consideration is hydrates. And we haven't talked very much about hydrates, but a hydrate is it looks like ice, and it kind of is. It is water and gas and high pressure. You put those together and cold temperatures, water will actually encase the gas molecule, and you end up with something that is an ice plug that actually has natural gas in it. So they can be kind of tough to deal with. So because you're opening and closing a valve, and when it just starts to flow, it's going across a very small area. Especially if this is closed and this is fully open, you're okay. But if you're just equalizing it and it's going through a small port, or you're partially open, there's a big restriction here, and you can get a lot of pressure drop. And when you drop the pressure in gas, it's going to get cold. So most times we'll put the subsurface safety valve deep in the well so that there's enough normal geothermal heat to keep from forming hydrates. So that's why a lot of times you'll see in wellbore diagrams or completion tallies the downhole safety valve being much lower than at the right at the Christmas tree. So back to this picture again. This is how we got here. This is the Santa Barbara event really focused innovation on how to avoid this happening again. So by being open-minded on where we can improve and considering the larger impact of our engineering choices, we'll drive innovation and continuous improvement. And hopefully we don't have to do it from learning from events. So we just need to stay open-minded and remember that the oil industry is an industry that continuously innovates. For over 100 years, there's been innovation to make things better in the industry, in technology and in thinking. So, yeah, that's it for me, as there's no further questions. So thank you for your time. I hope you found this informative. You can check out the rest of our webinar series, oil industry, on YouTube. It's at Valleycatter. And my name is Rod Gibbons, and I'll see you next time. Thanks, guys. Bye.